It's time to start. Welcome, everyone. Just for the record, this meeting is being recorded and later posted on YouTube. So just be advised, if you do not turn on your camera, you're likely not to be recorded, but your initials might appear. So if you have any objections to that, please note that this is being posted on YouTube. Welcome, everyone, to this edition of Verifiability Talks. It's my pleasure and honor to introduce Anna Cavalcanti. Anna is someone who doesn't need an introduction. I guess most of us know her already. She holds a chair with the Royal Academy of Engineering, and she has long-standing research in the application of rigorous techniques to various areas of software engineering. And in recent years, she has had very foundational contributions to engineering for software engineering for robotics, and she will be talking about that. So without further ado, I give the floor to Anna. Anna, thank you very much for having accepted, and the floor is yours.
Thank you very much for inviting me. It's fantastic to have the opportunity to talk to the consortium, and I see not many faces, but I see lots of names that I recognize, and I hope that there will be people that perhaps we will have a look at the talk afterwards. Because today what I would like to do is to set a vision that I have for work that perhaps lots of colleagues in this consortium or verifiability consortium will contribute to. So my research group is called RoboStar, so I'm talking about RoboStar technology. We have the impression that we are one of the largest, if not largest, group on software engineering for robotics in the world, with colleagues not only in New York, but now in Leicester as well, but Sheffield, Brazil, China, France. So it is a pleasure to be able to talk to you about what we have done. If I can move my slides. Sorry about this. I just managed to move my slides before. Yeah, what we have done, how we can improve verifiability, and I have also the honor to be part of the node for resilience. So how can we improve resilience as well? So today I'm going to talk about what is my perception of the current approach for the development of robotic systems. I will then present our approach, the RoboStar approach, and I apologize, I can recognize some people that are online here that we have seen, but there is nothing I can do. Our approach is something that we've been pursuing for a few years now and remains the same. So we will have seen already the first part of the talk, but I will then proceed to talk about the reality gap. I will proceed to see where I think the reality gap comes up and how we can use our approach and enrich our approach to deal with the reality gap. And in this point, I will be inviting colleagues to contribute and follow the approach that we have come up with. That to deal with the reality gap, one essential point will be to deal with properties of interest. So in our approach, properties need to be specified in terms of interaction. Properties at several levels, we will see there are at least 2 or 3 axes where we can, of the artifacts of the what I'm calling the modeling stack, will need to be defined, and properties in all these contexts needs to be unified to achieve a system view, but also to realize the view of the verifiability node on composition. Afterwards, having talked about the reality gap, we also put forward some ideas of how the humans in the loop can be considered in this context. If I have time, I'll then discuss the issue of physical modeling and discuss, to illustrate some specific technical work that we have done in the group very recently, and then I will finish with some future work. So I've given myself the task this afternoon to make the presentation accessible both to software engineers and control engineers in the room or online, and let's see how far we can go. I'd love to be interrupted and have a discussion while I'm giving the presentation, so please feel free to stop me and ask questions. The idea is to provoke some questions. So Current approach to the development in robotics. Some of you have heard me give me this vision of what is the current approach. My point is it's not compatible with the modern outlook of applications. While the applications in robotics are very advanced and we have a perspective of even more advanced techniques, the approach to software engineering is very, very primitive. So here on the left, I have sorry, here on the left, I can see that these slides haven't moved. Oh, okay. So here on the left, we have a sketch of what I believe colleagues do. First of all, if we are lucky, they develop a state machine. What I'm calling here in this drawing an abstract model, but it's not necessarily really abstract and not even a model. It is a drawing. And those of you that won't understand the difference between a drawing and a model, I would make the parallel. If you are trying to describe a building, a model is a sketch that you make on a piece of paper, and a model is something that you write using a CAD tool, for example, that understands the structure of a model and what it means to establish properties of that model. There is no such use of models normally in this community. There's no use of tool support beyond some drawing tools, which is not modeling tools. And once this state machine is established, colleagues use it as a basis for the first attempt to formalize the artifacts, which is the creation of a simulation. The state machine is used just as a reference to develop a simulation from scratch using a simulator tool that will have either a proprietary language or a low-level language like C++, and then coding and using the facilities of a particular tool for hardware and simulation is really the starting point, with the problem that there are loads of simulators out there. It's very difficult to have even portability at this level. Choice of simulation tool is not at all obvious. Time and probability normally recorded completely informally. So using the simulation, you may get some low-level code, and then people proceed on a trial and error basis, trying to use tests to ascertain some sort of guarantee about the behavior of that robotic system. But the fact is that in the end, there is no assurance. All that can be assured is that no error has been found. There is no assurance that there is no error. So what we propose to do in RoboStart with RoboStart technology is to change this scenario, which is plagued by what is called the reality gap. Reality gap being characterized when we are in this third phase of implementation, when we are developing the actual system, the behavior of the system does not match the simulation. Simulation is normally at the heart of the design approach, and that's where the gap is perceived, but certainly does not match an abstract model at all. So what is our approach? How do we want to change things? We want to change things by pursuing a model-based approach, where instead of these drawings for state machines, we have proper modeling languages. And in our group, we developed two languages, RoboChart and RoboWorld, for description of designs. This RoboChart is based on state machines with a component model that is simple and tailored for the area of robotics. RoboWorld is a controlled natural language that is tailored to specify operational requirements in controlled English about the robotic platform and the scenarios of the applications. And the approach is based on automatic generation of proof models, mathematical descriptions of the models, either as diagrams or in English. These proof models then be used as input for model checkers and theorem provers, which, based on properties of interest, can be used to ask some basic questions as to whether the model is valid. Validity here at this initial stage could be just core properties like deadlock freedom or live lock freedom, for example. And the idea is that if the model is found not to be valid, you go back to the models, never to low-level code. The idea is always to hide the mathematics from practitioners. And if validity is established, hopefully automatically at this stage, then again automatically we are generated a model for simulation. So our group has developed another modeling language called Robosim, now to model not designs in general, but simulations in particular, so cyclic mechanisms. And that language is supposed to be too independent. It is too independent, and it's supposed then to give you, to release you from this, from the burden of the choice of which robotic simulation should I use. The idea is that we would have it as a front end to several simulators. So using traditional robotic simulator, we'll then ask the question again, is my model valid? Is it valid now in the sense that the behavior and the simulation at least is as I expected? If it isn't, we go back to the models, potentially go back to the Robosim model, but hopefully the cost of going around the loop means that you go back to the RoboChart model and understand why the design has not behaved as expected. And then you go on with this in this automated and therefore low cost loop, developing the artifacts again. If it is valid, then you obtain deployment code. That deployment code will then be used for system testing. And in our approach, you derive the test cases also from the RoboChart models. So you already have in this series, you had another presentation from our colleague Rob Hirons, who talked about his approach to test. And that's a joint work with Rob. Rob is actually leading this work on the development of test cases from RoboChart and RoboWorld models. That test cases that can be used at the level of simulation, but also can be converted to use on the level of system testing, where perhaps observation and control are not so wide. So if the system under testing is correct, is not correct, if you have a problem, the idea of the approach, of course, you go back to models, never to low-level code. But if it is correct, the advantage of this approach is that besides the code, you also provide artifacts that can hopefully be useful to make a case for the quality of your work. So you would have proofs, you would have test results, you would have assumptions and environment assumptions about your system. So this is the RoboStar approach. What I would like to concentrate today is on the part of a system, the deployment code and the system testing. And why am I going to talk to you about this, about this particular part of the approach? It's because it is where the reality gap, which is something that I would like to focus on today, it's where the reality gap manifests itself. As I said, normally the reality gap comes when colleagues are in a trial and error approach testing the system. And at that point, they say, that's different from what I observed in simulation. But I suggest here that the reality gap is actually a phenomenon that we should address at a wider level. What I propose is that actually reality gap comes when, if I used even an organized approach like I've just described for you, I have proved some properties of the RoboChart of the RoboWorld models. I have proved some properties of my design, and I cannot observe them at the system testing level, as well as I established some properties, or I observed some properties at simulation level, and they were not observed at the system testing. So the reality gap needs to be handled, and I think there are several questions that I'd like to invite colleagues in this consortium to tackle with me, with this broader view of what the reality gap is. So the first question that we'd like to ask is already at the level of RoboChart. The reality gap here is, for me, about whether can we capture the essential aspects of the system already at this level. Is RoboChart the right language to be capturing the kind of properties that are worrying the colleagues already from the start of the system? Can we enrich the RoboChart library to make it more practical? So that is, for me, tackling the reality gap at the RoboChart level. These are the questions. When it comes to Robosim, at the simulation level, we have to ask, can we write the platforms and scenario models? So the reality gap is normally between the simulation and the system. First of all, can we write the simulation with the level of detail that I would like? And I would like to emphasize here the word of scenario models. Colleagues will be, and quite rightly, worried about the fact that we cannot model the environment. Absolutely. The environment is very rich and unpredictable in all sorts of ways. And modeling the environment, especially when we consider humans in the loop, that's not possible. But modeling scenarios is something that colleagues that work with simulations do all the time. So can we write platform scenario models appropriately in Robosim? That's another question that I'd like to invite the colleagues to address with me. Can we enrich the Robosim library? Should we enrich the Robosim library? At the RoboWorld level, now not talking about particular scenarios or particular platform, I would ask again, can we derive operational conditions in RoboWorld? Can we describe the operational conditions and the properties of interest in RoboWorld? And these three levels, RoboChart, Robosim, and RoboWorld, are extremely important. That's my message with this slide. There is no point in getting all the way to deployment and say, this is not what I expected, if you have not earlier on precisely described what you expected. So if you are in a situation where you have not recorded your design and your expectations of what are the operational conditions of your system, and all you have is that, that's not what I wanted to see, you are in a very weak position to start tackling this reality gap. So that is the message. So in deployment, there will be other questions. How much of the final code comes from the simulator? Which changes do we need to do? And how do we get traceability? If you're not in a position where you didn't even describe your design, describe your simulation, describe the operational conditions precisely, you cannot talk about traceability, which is, of course, property that everybody has, that so as being very important. You have nothing to trace back to. So it is very important to tackle the reality gap, start in an organized way, and what I would propose is to use the organized way in the way that I described so far in the RoboStar approach. So, sorry, these slides are getting stuck every now and then. So going back to the approach and to the issue of reality gap, I would like now to talk about properties. Because what is it that practitioners explain to us? That is not the system that I expect, that I now have a problem, it's the reality gap. Well, that is about, there were some properties, there was some, I had a simulation, an artifact, and there was some properties that I didn't observe. So another point that we will need to do is to define these properties of interest in an appropriate way. So this is the work that we are doing as part of this node, and what I'm going to present to you now is what are the thoughts so far in the last few months thinking about the issue of properties and how we are going to tackle this work that we have to do as part of the verifiability node. So properties of interest, there are several dimensions. So we have a whole work package that says we will define a property language. But actually, my point here is that we will have, in fact, a family of property languages because the problem has several dimensions. The first dimension that I would like to talk about is the dimension related to requirements. And from that, I believe we will get some important input from our colleagues in the resilience node. The resilience node has identified what, in a metaphor that Radu Kalinescu, who's the PI for that node, has described as sleek properties. Sleek properties in that context, they are social, legal, ethical, empathy, and cultural aspects of the autonomous system that need to be captured and verified. So I see a very strong overlap. For example, we have colleagues in our node work in the area of ethics, and I'm sure they will have great synergy with that other node there. So This is a dimension in the description of properties at this level, which is the level in which the users will be expecting to describe the requirements, that we will need to take into account, and that for an autonomous systems, they are extremely important. So Radu has a very interesting metaphor where he compares an autonomous robot or an autonomous system that is not aware of its social, legal, ethical, empathy, and cultural aspects of its context, to a person who comes from a different culture, perhaps a different country, and is found in a culture that they don't understand. In that context, they have less resilience, they have less ability to act because they don't understand what's acceptable, what's not acceptable. It's the same thing. We need to worry about these properties. So that's one of the dimensions that I would like to work in terms of properties. But there is another dimension as well, which is the technical dimension. The technical dimension will depend on the kind of component, the kind of artifact that we are trying to use, but also the kind of technology that we are trying to use. There are core properties, there are technical properties like deadlock freedom, live lock freedom. There are logical properties if I'm using a tool or a technique that is based on the use of some form of logic, CTL, PCTL, whatever. There will be refinement properties if I'm using a refinement technique, as we are in the Robustar group. There will be properties that will be related to the application domains and to properties that will be related to the tools. So with all these requirements, what are the design directions that we are following for the design of the language, our property languages? It is compatible with the Robustar technology, of course. We would like to hide the mathematical language. So you can see here in this diagram, in the same way that we are going to automatically generate proof models from the design and operational requires specifications. From the properties of interest, we're also going to automatically generate proof models, and both will be used as input for the model checkers and theory provers. So that is the first thing. We want to use to hide the mathematical language. But more than that, we want to use the language of the design models. That is something the practitioners sometimes do not observe with this part of the reality gap. It's part of the problem that they face in terms of the reality gap, because there is a gap also in terms of how they specify, how they understand and have an informed understanding of a property, and how that property manifests itself in their artifacts. So in the Robustar technology, we have a focus on interactions, but we also have a collection, a certain structure. And I'm going to present to you now what I'm calling the modeling stack that will allow us to deal with the reality gap. So the modeling stack has at least two axes, if not more. And I am going to start by talking about the decomposition of a system along the scope axis. And I am going to talk about this at the level of Robosim, at the level of simulation, because practitioners, robotic developers, they start, hopefully, well, many will start writing some code for a particular platform and deploying the platform. But I'm assuming that many of them will start writing a simulation. So when they write a simulation, it is our proposal that they don't tackle that problem by writing some C++ code for a robotic simulator, but that they describe it in Robosim. And in Robosim, we'll have three main artifacts. We'll have the description of the control software at the simulation level as a cyclic mechanism. We have the description of the physical model, and we have the description of the scenario. Traditional simulations won't make very clear distinctions of these 3 points, and at my point that we must, absolutely must, if we are to have a chance to deal with the reality gap. And let's look at each of these artifacts. So when I'm describing the control software, the cyclic mechanism, one thing that we should strive for, and that is provided in Robosim, is platform independence. At that level, I will want to say what is it that my control software needs from the platform, what are the services that it requires from the platform, but I don't want to be specific about platform. So in the Robosim modeling framework, what we have is a notion of platform that is basically just a description of these services. We describe services as variables, operation and events. So here I have a small example of perhaps a little robot that moves around an arena, avoiding obstacles. It could be a vacuum cleaner, for instance. And then in this case, what I have identified here is an event called obstacle that takes some data, perhaps left the direction that it's seen where the obstacle is. And I have an operation move that sets the robot at a certain speed. What do these things do? They are representing sensors and actuators. They are representing the fact that my software expects that the platform is able to detect some obstacles in its direction, but it's not telling me how. The same way, it is saying that my platform is expected to be able to move, but I also am not saying how. It could even be flying. It could be using all sorts of technologies to move. So the software is completely independent. What it means is that at this level, I could write properties if my model is timed, which it can be. I can write properties like, if my robot detects an obstacle, after a certain time of units, it will call an operation move. But at this level, I won't be able to say anything about what is the effect of calling that operation move. That is not what can be done at this level. On another level, if I want to worry about the physical description, then I will have to describe a physical model. At that level, roboticists are happy to talk about concepts like links, joints, sensors, and actuators. This is something that is not at all strange for roboticists. And I need now to have, I can now have a completely different description of the same kind of input and output. So my physical model would, for example, take as input some infrared light, because it has an infrared sensor that will then trigger a certain voltage. That's my sensor that can be detecting obstacles. My robot, my physical model, will also have a motor that when we give a desired speed, that will have some sort of a way of interacting with that motor by defining the desired speed, it will produce some torque. So that's an entirely different view of the platform. And what we need to do, if I want to establish the decomposition of the system in these terms, now is to establish a platform mapping. I have to explain how the outputs of sensors, they are related to the inputs of my software, for example, the input of the obstacle input. In the same way, the other direction, if I have operation move, that is an output of my software that needs to be mapped to an input for the actuator of the physical model. And the moment that my scope for my system now includes the software and the physical model, that now we have the chance to prove other kinds of properties. Now we can say, if there is an object that is providing a certain infrared lights, after a certain period of time, there is a certain rotation that's induced on the wheels of the robot. So it is a different scope and therefore a different language that I can have to describe my properties. And now I can talk about, here at the control software level, I didn't have a way of explaining that perhaps my sensor has some unpredictable behavior. That is not there. That is not in the control software model. That would be in the physical model. That's where I would describe how my sensors work. And roboticists do that all the time. They take a sensor out of a box, they experiment on the lab, they fit some curve to give me some equations that would be captured in this physical model. I could have richer models, but they will have to be completely separate from the physical model to achieve some understanding of some compositionality and some understanding, some chance of pinpoint where the reality gap might manifest itself and therefore can be treated. In the same way, I would have in Robosim a way to describe a scenario model. The scenario model will describe some quantities and events of interest, for example, position objects and robots, and I would need to describe then the effects on inputs and sensors, the colors of those objects, the force that the motor will induce in moving the objects. And then I would need, moving the robots. And then I would need an environment mapping in the same way to explain how object properties affect infrared light, for example. So this decomposition, it is strange when we're talking about the simulation, but it's just a reflection of the reality. If I'm talking about the deployed system, of course I have the software, of course I have the physical model, of course I have my environment, which is being captured here in the scenario model. So the message here is that separation that's natural in the real world, it should be reflected at the level of modeling as well. So this is simulation level. At the design level, we have RoboChart and RoboWorld. RoboChart, and then in this case, we have something that is, I found it quite interesting. The workflow that I expect to happen is that colleagues might start with a RoboChart, which is an interrupt-based design where you're not worried about cycles, and derive that control software automatically. However, for physical and environment modeling, we would expect colleagues to start at the simulation level and then abstract to some operational requirements, understand that system at the level of simulation, and then understand what are the assumptions that I'm actually making. I have tried at simulation arenas of several sizes, arenas with several inclinations on their floor, for example. I have played perhaps even with different platforms at simulation. What are the actually operational requirements that I can have? So in RoboWorld, what we are trying to do and what we have followed so far is to say, okay, we are at a different level of abstraction. At this level of abstraction, for example, we will assume that my robot is just a dot. There are some abstractions that are made like that in the simulation, but those abstractions are recorded by understanding that they are abstractions. And how do we do that? Is by keeping this structure, that, in fact, in RoboWorld, I am covering a platform mapping, a physical model, an environment mapping, and a scenario model, or a collection of scenarios. That this here we will have assumptions about them. And what I'm posing to you, and that's certainly true at a mathematical point of view, is that the mathematical model that is generated from Robosim and has some structure, that same structure should be used for the mathematical model for RoboChart and RoboWorld if we are to have a chance to establish some sort of traceability. And if I have made some assumptions here, for instance, that my physical model is such that my robot is a dot, that is recorded in the physical model and in the platform mapping. If I am assuming, for example, that I'm not interested in the properties of a sensor, that I assume that I can somehow get the obstacle information directly from the position, and therefore I have sensors that are perfect, that is still recorded here explicitly. Otherwise, I don't have a chance to challenge the assumptions because they have not been said. So that is the proposal to the level of RoboChart, of design, RoboChart and RoboWorld. And my proposal is also that at the level of the simulation code, that is hopefully automatically generated, at least a sketch of it is automatically generated, we keep that structure. Simulation code these days, if you get simulation that's written by colleagues, it has a notion of world, and in there you have everywhere a complete solid monolithic description of what is the software, what is the simulation of the platform in terms of physics engines, and what is the simulation of elements of the scenario also using physics engines. Our proposal for even the automatically generated artifacts is that the simulation code, perhaps at the level of the software, we have some C++ or Lua or whatever language you have, but you have a separate description of the platform, and we are pursuing descriptions in a domain-specific language called SDF, but it could be URDF. It's an XML-based language that describes physical models at this level. doesn't capture equations, it uses physics engines, but that separation should be kept. The same thing, we should have a separate description as well for the environment using whatever domain-specific language. With the implementation of these mappings, also again completely explicitly said and understood. It's only in this way that we have a chance to establish some traceability. Let me give you an example based on a case study that we are working on now, which is a case study of a simple Segway. And what we are trying, my colleagues and I are trying to do, is to reverse engineer this Segway that we got out of a box. It comes with the platform, it comes with some hardware, and we're trying to reverse engineer it. And here's the nightmare if you want to have some traceability and therefore tackle the reality gap. So if I look at the hardware that comes with the little Segway, it has an inertial measurement unit, a particular piece of hardware that includes an accelerometer and a gyroscope. That has also comes with a library. And to deal with the accelerometer, with the gyroscope, and get information about the speed and about your pitch and roll of this Segway, we have some methods. We have a method get motion that gets information directly from the accelerometer. We have another method, angle test, that applies a Kalman filter and then sets some variables, some fields in an object of type Kalman filter. So we have variables angle, gyro X, gyro Y, and gyro Z, which are used in the code. That's at the deployment level. That's where our colleagues would find the reality gap. Well, first thing that we try to do, well, we reverse engineering. Let's write the simulation. Simulation, it has separate accelerometer and gyroscope, the Copilia-Sim, which is the particular reactive simulator that we are using. It has separate support for use of accelerometers and gyroscopes. And the different notion is the notion of a communication tube. This gap, this break in the way in which you deal with these things is something that needs to be recorded. It's something that needs to be understood, and we need to establish that if we don't establish the relationship between these different levels of abstraction, we're lost in terms of traceability. And then when we come to RoboChart or Robosim, then we can say, okay, now I have, for example, input events, angle gyro X, gyro Y, and gyro Z. And those input events are the events that we're going to use to specify their control software, and they can be realized in a simulation using these communication tubes. And when I get to the actual system, I will have all this a nightmare of the implementation of the actual platform. But if I need to identify that to be able to establish the traceability at this level. So what we end up, if we follow this practice, is with this modeling stack that allows us to tackle the reality gap. How does it allow me to tackle the reality gap? It allows me to tackle the reality gap because when colleagues are trying to define some properties, here at the level of the scenarios, or at the level in RoboWorld, talking about not particular scenarios, but talking about environment assumptions and elements of the environment, the objects, the arena, the obstacles that are found, then I have, via these mappings, a way of translating those properties to talk about the system in the physical model, and I have a way of translating those properties to tackle the relevant software properties. And if I have the stack that I built by understanding how the different levels of abstraction match, then I will be able to move and understand I'm having a problem in the deployment code. How can I use what I know about Robosim or even RoboChart to tackle that deployment code? How can I establish traceability? How can I pick up, for example, the result of a test and then bring it back towards the stack to get all the way to RoboChart and say, that test here, what does it mean in the RoboChart model? Does it fail? Is it a problem of my design? Or have I made a mistake in terms of the reality, not a mistake, or have I made some abstraction, some assumption that's not valid? That kind of conversion, that kind of traceability along these two axes can only be achieved if we are careful in the way that we establish compositionality at this level of granularity. So, of course, mathematically, we need to have everything unified, and we are working as a group in that sort of unification. And Jim Woodcock has already presented another seminar also in this series where he described his interest in the unification, and that is about making sure that, my understanding is that this is about making sure that we have behind the scenes of this modeling stack a mathematical framework that can establish all these relationships that I'll be seeking for in my property languages. So what has been done in terms of this unification for the control software in Robosim, we have a semantics in a version of CSP called TalkCSP, for which we have created a novel semantics that is not just trying to reuse existing semantics of CSP, because there were some problems in achieving the sort of properties that we want. And that is fine for the control software. For the physical model, we have to use continuous understanding. We could use, for instance, dynamic logic. And that means that when we are talking about the artifacts that encompass both the physical model and the control software linked by the platform mapping, we need a hybrid language, and what we use in Sci-Fi Circus. And so Sci-Fi Circus allows us to deal with the notions of interaction that comes from the view of variables, events, and operations that is discrete in the control software, but allows us to deal with the dynamic behavior that is typical of physical models as well. TalkCSP is also used to give semantics to the software in RoboChart, and because we have that unification, we are able to compare the interrupt-based model that comes from RoboChart with the cyclic mechanisms that come with Robosim. For RoboWorld, because RoboWorld will be reflecting the view of the physical model in the environment, we will have to be using Sci-Fi Circus as well. And of course, time and discrete and continuous time is just one of the dimensions that we need to use in our work. RoboChart also has a semantics in Prism, for example. So we have a tool called Robo2 that provides support for RoboChart and as well for Robosim and RoboWorld under development, that generates code or the proof models, as I described at the beginning when I described the approach in CSP for FDR, but also in reactive models for Prism. And as Jim already described, we will have to tackle the issue of unification. How do we understand and relate models in CSP or TalkCSP with a particular view of time, or Sci-Fi Circle with continuous time, and models in Prism? And we will need probability along the axis of scope for several reasons and different reasons. So at the level control software, we'll be interested in probabilistic algorithms with some colleagues. At the physical model, we will be interested in capturing perhaps tear and wear and noise in the platform. At the level of the scenarios, we will be able to capture some uncertainty in the environment. So I just wanted to say that with this, we cannot work entirely on the Sci-Fi Circus world. Sci-Fi Circus has a basis in the unifying theories of programming, which is what established the connection with the unification agenda, and will allow us to answer the questions for probabilistic behavior as well as timed behavior. So to summarize, the property language that we are designing is not a property language. It is a family of languages. And that family of languages will cover the scope axis, talking about with properties that are of interest at the software level, that are properties that are of interest at the software with hardware in the loop level, describing properties of links, joints, sensors, and actuators, so entirely different domain, entirely different language, as well as properties at the environment level, and in the several levels of abstraction as well, properties about the deployed code, where colleagues will find the reality gap expressed in terms of very low-level problems, all the way to properties at the level of the design, where we find operational requirements and robocharts. So those are the two axes that we identify, but there are more. It's a three-dimensional, four-dimensional world, because we also need to specialize these languages to application domains, and that I'm hoping will be via libraries, but also specialize the language to tools. So it makes no sense with colleagues in this consortium or in the scheme as a whole are interested in tools. Our language will be have to be rich enough to deal with the tools that are of interest. And of course, so far, I have looked at the control software as a black box. And ideally, I will look at the control software and think about compositionality at the level of the control software as well. And I hope that's something that we'll have scope to get into in this project as well. All the languages, I envisage that we'll have a mixture of diagrams and controlled natural language, and that they will have, of course, a unified semantics. And how about the humans? So far, thinking about the verifiability node, I also have a responsibility in terms of the work package that I'm leading, interacting with colleagues that will be worried about human behavior. How do I envisage that we will be able to interact? And we have been talking to Thalys and to colleagues in the Department of Psychology in New York that I would like to bring to work with us and collaborate in this node. The humans, they are in the scenarios. They are part of the environment assumptions. The humans, to model the humans, we will need to identify in that modeling stack what are the quantities or the events of interest. And I won't have the expertise to do that, and I hope that colleagues will tell me. They have already told me, given me some examples, quantities and events of interest for them, tiredness, familiarity with the system, the expected behaviors, depending on the stakeholders. They could be teleoperators, they could be users, they could be passers-by. I'm told teleoperators are the ones that are easiest for us to try and predict, because we can train them and have some chance of describing what the expected behaviors are. But even so, the behavior will be affected by tiredness. Their behavior will also be affected by what they call practical drift, which their familiarity with the system and the expectations of behaviors and misbehavior of the system. And we cannot model the human just like we cannot model the environment. It's part of the reason why we cannot model the environment. But we can model assumptions. We can describe the assumptions about the behavior of the system, and we can bring them into the modeling stack if we focus on how do we expect that they will interact with the system. So the notion of interaction is throughout all the modeling stack, and is absolutely fundamental for us to be able to tackle this problem. How do we get the data to inform the models? I'll leave it for the psychologists, but I will help. That's why it is there in italics. How can we write the models and assumptions as part of this scope of this language? But we need to understand what it is. So Robo2 hopefully will be a very valuable starting point for this work. It's been supporting our approach. It's been used in several interesting case studies, and I hope that we will bring the property language to enrich that ecosystem and perhaps be richer. Of course, I am very much interested in robotics and autonomous robots, but not every autonomous system is a robot, and that is a language that is where, in my view, what happens is that the modeling stack can be simplified, but we will still have a modeling stack to deal with. So what's next? Robosim and RoboWorld, they are under development, being implemented as we speak. We refine the techniques to connect both those two levels of Robosim and RoboWorld, covering both the software platform and environment, soundness being established in case being driven by case stats. Support to the user will be my focus in the work in this node. The development of properties language, modeling of scenarios and environment assumptions, and test generation working together with Rob and his team, but focus on the properties language in terms of following these ideas that I've just described. The work that I described is not my work. It's work of a team that I'm very lucky and very honored to be able to collaborate with. Loads of people, as I show here, there is a 3 dots. They don't fit in one slide, but here are some of them. Okay, so I think I will stop here and leave some minutes for questions, and I'll talk about physical modeling some other day. Okay, thank you very much.
Thank you very much, Anna. So we have time for a few questions. Are there any questions from the audience? Yes, Jan. Well, we have 2 Jans. So Jan Oliver Ringers first and Jan Peleska.
Yeah, it's Jan Peleska. Thank you very much, Anna, for this exciting talk.
Thank you for attending. It's so lovely to see you, Jan.
Of course, I have hundreds of questions, but one is, I think, the most exciting from my point of view. In your exposition of the whole workflow from robot charts to simulation and so on, there were several situations where you were dealing with discrete information and then with time continuous information. You talked about circus sci-fi, and I think this can cover hybrid aspects in the semantics. Is that true?
Yes. Yes.
And my question is, do you have a specific point in this complete workflow model that you showed first, where you go from time continuous behavior to discretized behavior, or do you go back and forth several times in your whole workflow?
Okay, so let me see if I can answer the question. I'm not quite sure what you mean there. So the semantics is, I have a slide here that I didn't have time. So here's the Robosim semantics that uses sci-fi service. What we have is that a part of that modeling stack on the horizontal. Here we have the control software model. It's in this picture here. It's called the D model. It's the data model. And this model has a CSP semantics that is a TOC CSP semantics. It's time, discrete time, but it's reactive semantics. The P model, which is the platform, the physical model, that's what we call here, that is a continuous model, a system of differential algebraic equations. And then when we put this together, then we have to have a cyclic view of the interaction between the platform model and the data model. So we have a cyclic model because the software is discrete and will remain discrete. Our understanding of the semantics of the software is that discrete mathematics, and it remains like that. So we have here in parallel that discrete process with a hybrid process where evolution guided by the equations is interrupted so to speak, every point of the cycle to understand how the inputs affect those equations, how the outputs of those equations will affect the events, and therefore produce communication that will affect the other side. So the model of the software is always discrete. The model of the component that is hybrid. And so the workflow does not see it going back and forth and forth. The idea is that with compositionality, if I decompose a property, I will decompose it and get to some property about the software that's completely discrete. If I have a property about the system, that is a hybrid property, and we should be using not FDR anymore.
Thanks very much. This is a very nice slide explaining your approach very well. Thank you.
Thank you.
Thank you, Jan, for the question. The other Jan, I'll ring it. Would you like to ask your question?
Okay, yes, thank you. So I have a question about one of the very early slides where you showed this approach. You start with a model, and then you go maybe through some translation, and then you have a model checker, you have valid yes or no. The yes case, everybody's happy, but the no case, you have to go back to the model. So usually when you get from a model checker that there is a problem, you get something like a counterexample. So do you have any nice way of transforming that back to the model level?
No, for lack of time. My colleagues in the team are always very disappointed because they think, wow, we get model checker, we used more extensively as FDR. That comes and gives you an FDR because of the CSP paradigm, and our paradigm is based on CSP. Everything that it tells in terms of counterexamples are based on events, and these events in the semantics, they correspond to setting values of variables. They correspond to events of RoboChart happening, inputs or outputs, and they correspond to operations being called. So it is a technological issue that we haven't done, but I would say it's a technological issue to pick up that counterexample and translate it into the variables, events, and operations of the system in RoboChart. What is the challenge? The challenge is that the proof model, the semantics that you create, is compositional. Compositionality is the back of all that. So if you, and the notion of interaction is pervasive as well. So if your system in RoboChart or RoboMode is based on interactions, that notion of interaction needs to be reflected directly in the mathematical model. We need to have an understanding when we create these proof models of how those concepts, the visible behavior of a RoboChart model is captured in the semantics, and then you can do it. So I would say it's not easy. The difficulty needs to be addressed on how you construct the proof models, so that the tools, when you're making the proofs, when they speak to you, they speak in a language that makes sense for the components of your model themselves, and then you can do it.
So this means it could be that some of your proof models that you generate don't have this property of the backwards compositionality that you would need?
No.
Because we had an example where we basically did a translation and then we failed to trace it back, and it was because the original step where we go, this proof model step, already was violating some principles that allowed us to translate it back. But this is the case for you as well, or you think there is no problem in the way that you are right now generating the proof model?
Look, there is no problem is a bit too strong. So what I was saying is the compositionality and the interaction view that we have of the RoboChart model is replicated in its semantics. That's no easy feat. We've done it. Because we've done it, we have this one-to-one match. If I get a counterexample out of my model checker, I can directly relate that to the diagram.
Okay.
That is not easy. The difficulty is getting the proof model with the right compositionality. What is the problem of that? Is to replicate that structure of the high-level model for the model checker introduces inefficiencies. And some approaches will then say, let me now optimize the mathematical model to let the model checker work. When you do that, you lose traceability. So there is a compromise to be made. And for these and several other reasons, theorem proving is going to be extremely important. And I would say you lose traceability when you optimize the mathematical model. If you don't, and you give a semantics that is compositional with respect to the constructs of the original language, you obtain traceability. That's how you do it. But it's not trivial.
Okay, thanks.
Okay, we have one more question from Colin. We are a bit over time, so Colin, it would be great if you could keep it a bit short. Thank you.
I'll try. So Anna, in control theory, when you come to the actual physical system, you can have instabilities that arise, hunting behaviors, which are to do with the control theory rather than any higher level control software, which is kind of planning, is more what you're talking about. Is that sort of issue outside the scope of what you're doing?
I wasn't talking particularly about planning. Or when I was looking at the control software, our view of what the control software is that it is the complete stack in that direction as well. As I mentioned, that in this discussion, I looked at the control software as a black box, but it has a structure, planning, executive, and low-level control, which is what you're talking about. Colin, I wouldn't like to leave it out. Not to say that I will be able to sort everything. That is, for me, part of the research that we are going to be doing here. But if I can go back to perhaps that is my view at the moment of this kind, the need to record this kind of discrepancy, the need to understand. When I was in robot chart model and I defined that I have 4 of these events that are give me an input, it means that I am saying absolutely nothing about my sensors. And the same thing would be about my actuators. I will be saying I'll be calling some operation that will deal with the motor and so on, and I'm assuming perfection. If I don't have an understanding of how those abstractions map to a simulation and or to what actually happens in the code and in your low-level control, I won't be able to pinpoint even what is the abstraction that I've done that caused the problem. Okay,
so what you're saying is right, but what I'm saying is more fundamental than that, is where intrinsically it's a cybernetic control theory problem that certain things. So, for example, this example, they've avoided all that issue in terms of they've found a control solution which is stable, but often you get instabilities. I mean, that's the big thing about in terms of control theory, is trying to do simulation and analyze and using Nyquist diagrams and so forth in order to be able to avoid those sort of things. That's what I mean. Is that outside the scope of what, or where would that occur?
That for me is coming from the testing work. Well, and that I think your question, Colin, is related to a question that I get very, very often from people that don't have the knowledge that you just described there, and look at me and say, if you already proved, why do you need to simulate?
Yeah.
And what you just described is exactly the reason I understand people need to simulate. So what in this workflow here, what I'm expecting is that this first point where you ask the valid question is high-level properties, deadlock-free, live-lock-free, and then you go to the simulation, and then you're going to face these issues that you are mentioning, and there will be design space exploration techniques, which I hope the Rob with his testing techniques will help to make the design space exploration, the simulation, find what is the right system, go back, fix the parameters that they need to achieve the stability, and check. Now I have more confidence, more properties that I believe are valid. I'll prove again. I expect colleagues to go around this loop at least twice because I'm very optimistic. So yeah, absolutely.
Okay.
I think what you just described is the reason why we need proof and simulate.
Yes,
absolutely. And it's so nice to get that question instead of the naive one that say, if you proved, why do you simulate? Thank you.
Okay, thank you very much, everyone. I don't see any raised hands, and we are a bit beyond our time limit. So thank you very much again, Anna, for this very informative talk. Lots of different aspects to be addressed, and lots of interesting research to come, and lots of interesting results already there. So thanks again. We will meet in 2 weeks' time again with the next verifiability talk, and there Effie Law will talk about something that Anna also mentioned towards the end of her talk about modeling human behavior, and see what it has to do with trust, how we can do that, and how we can use it in order to increase trust in such systems. Thank you very much, and see you in 2 weeks.
Thank you.
Thanks.